Part 1 guaranteed you'd never seen sentence semantics approached in such a radical way before. Part 2, dialogues and mental models, has even more surprises. So keep that seatbelt securely fastened. It's going to be an equally bumpy flight.
Definition of the mental model. Let's look at the mental model first. There are various definitions of the mental model. Here we define the mental model as a simplified abstraction of the real world, which we hold in our minds to assist us in our lives. Exactly what this involves will become more apparent as we proceed.
Our own mental model is established and updated using data from all of our senses. But here we consider just a small part of a mental model, established, updated and queried using an English language dialogue only.
In early school, we encountered reading comprehension exercises involving reading and comprehending a simple description of something, followed by responding to queries, testing that comprehension. For example, a lady has 2 Burmese cats and 3 Siamese cats. Each Burmese cat has 3 biscuits and 2 toys. Each Siamese cat has 2 biscuits and 3 toys. Count each lady, each cat, each biscuit and each toy.
To solve this, we built a mental model of the situation from the English sentences and then consulted the model to form sentences responding to the queries. In this lecture, we're going to study mechanisms allowing us to do a similar sort of thing. In fact, the software application, AI Dialogue, which is described later, is able to understand and respond correctly to the example given. Our study of dialogues and mental models will show us how it is able to do this sort of thing.
From part 1, you may have started to guess that we can use a semantic network as a foundation for our restricted mental model. This is not necessarily the way our brains and minds hold our own mental model, but it does give similar results in comprehension exercises, as we shall soon see.
Semantic networks have a long history of use in linguistic semantics. To the left is a typical network representing the station example from the Part 1 lecture. You'll notice that in the diagram, the links between nodes represent fairly complicated concepts. For example, is above, is beside, and is below.
But in part 1, we adopted a very rational network representation by allowing only is or has on the edges linking nodes. This became possible because we showed that most English sentences could be reduced entirely to sets of simple is and has expressions. That is, X is Y and X has Y, where X and Y were sentence words. To the left, we see the resulting rationalized network.
Let's now have a look at the general form of the sentences within a dialogue from which a mental model may be built. Sentences generally have 2 components. One specifies new data to add to the mental model, and one whereabouts on the mental model. For example, with the sentence, "The Siamese cat is very fierce," the Siamese cat phrase picks out our Siamese cat data location on our own mental model, and the "is very fierce" phrase gives new data to add to our mental model at this location.
To put it another way, This is very much like updating an IT database. The following is an example of an update to such a database using the IT database query language SQL. Update pets, set character equals is very fierce, where breed equals Siamese, and type equals cat. You don't really need to fully understand this to see how it resembles the structure of the previous sentence.
In practice, of course, our own mental model database is far more versatile. Our mental decoding of the content of English sentences allows a much more flexible data input. But a problem which arises with complex sentence clause structures is that the location on our mental model and the data to be added at that location tend to get all mixed up. Some complex sentences may in fact mention multiple locations on our mental model with multiple data updates associated with them.
For example, the sentence, Jack and Jill each climbs up the steep hill, where Jack and Jill and steep hill already exist on our model, involves separate updates to all three locations. The Jack and Jill locations are updated with climbing, that is up, and the steep hill location with the two instances of climbing. Sentences with complex clauses can involve even more convoluted updates to our model. Shortly we will examine in detail how such updates may be carried out.
Sometimes there's no specific model location given in a sentence, as in, there are 3 Burmese cats, which means we just add to our model this fact and in practice create 3 new data locations for future new individual Burmese cat data.
In other cases, a sentence introduces new data and implicitly provides a location for further data, as in the sentence, a dog has a bone. Here, a dog adds an instance of dog to our model and provides a location for the data has a bone.
A final component of a sentence is its truth or falsehood. In our terms, we ask, does it represent a proposed valid or invalid update of our mental model? If it is a proposed invalid update, then can we detect that this is so and avoid adding erroneous data to our mental model?
This is a significant topic, dealt with only briefly in this particular lecture. Just a couple of points. We can only determine validity in the context of our model, not in the context of the real world. If a sentence refers to a second cat with only one cat present on our model, we can detect that this is invalid. But if a sentence declares there is a king of France, we generally have to assume this is valid, because our knowledge is limited to just what any dialogue contains.
Let's try to clarify things a bit now by examining in detail the steps in building, updating and querying our mental model. Again, this is not necessarily the way our mind and brain does the same job, but as we shall see, it does give us a system that we can use for study purposes.
Suppose the first sentence we ever encounter in building our model is a lady has 3 cats. The first step is to reduce this to is and has expressions alone, as we saw in part 1.
Below, therefore, from the part 1 lecture, is the is-has analysis of a lady has 3 cats. So we've got lady has cat, cat is first, lady has cat, cat is second, lady has cat, cat is third.
From this analysis, that is, lady has cat, cat is first, lady has cat, cat is second, lady has cat, cat is third, we can build a left-hand semantic network. This constitutes the initial content of our mental model.
Suppose we then encounter the sentence, the second cat is very wayward. This is an update or augmentation of our previous mental model data. So how do we go about modifying the model to add in this new information?
Again, the first step is to reduce the sentence to is and has expressions alone. The sentence, the second cat is very wayward, has the analysis from part 1 of cat is second, cat is wayward, wayward is very.
As before, we build another network. So the analysis of the second cat is very wayward gives us cat is second, cat is wayward, wayward is very, which results in the left-hand network. But note that we have distinguished the phrase the second cat and the corresponding part of the network.
This is because the phrase the second cat is headed by the definite article the, implying that what follows is something already present on our model. It is giving us the location on our model for the new data. This will eventually cause us to search the model network until we find that part of it matching the node edge pattern lower left.
But this is not the end of the story. The network for the second cat has a distinguished node cat, shown lower left, surrounded by dashes. This is the subject anchor. The subject anchor corresponds to the sentence subject root. The cat is the something which is very wayward. The upper left is very wayward network is new data to be added to our model. But note at the cat node rather than the second node.
But again, this is not the end of the story. The network of is very wayward has a distinguished node wayward, upper left, surrounded by dashes. This is the object anchor. The object anchor corresponds to the sentence object root. Note this is the attachment point wayward, for very wayward rather than very.
And the final component of the process is the attachment edge, is, corresponding to the sentence main verb. We generally separate this out from the object phrase. The main verb is always is or has, as we've seen from the part 1 analysis.
We can therefore update the network as shown to the left. Note that the connection points are at the nodes cat and wayward, not at the nodes second or very. The connection edge is the main verb is.
Let's review the sentence processing we've just done. It generally involves building a semantic network for the sentence subject and another for the sentence object or complement. We refer to these small networks as subnets. For brevity, we then refer to the main semantic network corresponding to our mental model simply as the net.
If we encounter the sentence, "The Siamese cat is very fierce," then we form the subnets shown to the left. The lower subnet is the subject subnet and the upper one, the object subnet. We have also separated out the main verb is, shown in the middle.
Associated with each subnet, there is generally an anchor node, shown dashed in the figure. If the subject anchor was absent, we would not know whether to attach the new data to Siamese or cat when we found these on the net. If the object anchor was absent, we would not know that the new data attachment point was fierce rather than very. The verb then tells us the attachment edge type is or has.
Moving on now, let's see how we can query our mental model. Suppose we encounter the sentence, "The lady has how many cats?" Can we manage to create a reply to this?
Again, the first step is to reduce the sentence to is and has expressions alone. The sentence "The lady has how many cats" has the analysis "lady has cat." But here there's also some metadata not represented in the analysis, indicating that this is a query. The corresponding subnet is shown below left.
We then search our mental model net to find any pattern that matches the query sentence subnet pattern. As we can see to the left, we get 3 matches, so we can reply to the query, "The lady has how many cats?" with "The lady has 3 cats."
Let's just pause for a moment to compare sentence semantics and sentence syntax. Very syntactic aspects of sentences need not be represented directly on our mental model. These include plurals, indefinite and definite articles, and anaphoric references. Let's examine why.
Firstly, plurals need not appear on our model. You will have observed that all net nodes are singular. This is because plurals in sentences largely represent purely syntactic information, which is generally semantically redundant.
If we say 3 cats, we really know cat is plural because of the 3. We could just say 3 cat. Sounds a little bit strange. Occasionally the plural is significant, as in Jack has apple compared with Jack has apples. We can solve this by adding quantity and number nodes to our model, as shown to the left.
As you will have seen previously, we often create separate instances of a number of items. For instance, in "A lady has 2 cats," as in the upper left, but we do not have to, as in the lower left. It depends on subsequent usage on our mental model.
Similarly, all node linking edges so far have been is rather than am or are, and has rather than have. Other declinations associated with tense, for example was or had, disappear because, as we've seen in part 1, tense is flagged separately.
Indefinite articles such as a or an or three are associated with adding new data to our mental model. For example, if we say a lady has 3 cats, we add the lady and the 3 cats to our model.
In contrast, definite articles such as the or each are often associated with locating existing data on our mental model net and updating or augmenting it. For example, if we say the second cat is wayward, we need to locate the second cat on our model and then augment it with the data that it is wayward.
But we sometimes use a definite article like the informally to add new data rather than to reference existing. We can check which is the case by searching the net for the data referred to. If absent, the data is new, otherwise it is existing. If more than one existing data instance is found, we know the sentence is ambiguous or invalid.
Just looking now at anaphoric references. Anaphoric references need never appear on our model because, for example, he has the pail is replaced by Jack has the pail. This means that none of the pronouns he, she, they or it needs ever appear on the mental model. This also applies to possessive and accusative versions of these. That is his, hers, their, its, him, her, them, and in conclusion, it.
Although, as we've just seen, plurals, indefinite and definite articles and anaphoric references are absent on our model, this doesn't prevent us from synthesizing grammatically correct sentences from the model when we need to. We still have enough information on the model to form cats from cat, to form a or an, or the, or each as needed, and to abbreviate Jack to he or him when appropriate, and so on.
Let's resume now and have a look at a more complex query on our model. Suppose we encounter the sentences Jack, Cole and Humpty each like Jill, and then subsequently the sentence Jill likes Jack and Humpty. This situation is illustrated in the figure to the left.
After the sentence Jack, Cole and Humpty each like Jill, our model net from part 1 is as shown to the left.
After the subsequent sentence, Jill likes Jack and Humpty, our model is augmented with data as shown to the left. The new data is added into the right place using the search and anchor techniques which were described earlier.
Suppose we then encounter the query sentence. List each person that likes Jill, that Jill likes. How can we tackle this and derive an answer to it?
So we begin as always by reducing the query sentence to a series of is, has expressions, as below. Jill is liking, person has liking, liking of person. Person is liking, Jill has liking, liking of Jill, and building the corresponding sentence subnet, shown again to the left-hand side.
The node person is special when we start to search the net. The node person will match anything. It's like a wild card. Not only that, but the actual nodes that person matches during the search are of interest, and we need to know about them and record them.
So the subnet above has the matches shown circled to the left, and from these we can see that person matches Jack and Humpty, but not Co.
So we are able to reply to the query, list each person that likes Jill that Jill likes with Jack and Humpty, as person matches these.
Let's now have a look at an example of an assertion. Suppose we have an assertion such as Cole likes Jill, and we need to determine its truth or otherwise. We again begin by reducing the assertion to is, has expressions. So these are Cole is liking, Jill has liking, interpretable as liking of Jill.
Then we form the subnet above from Cole is liking, Jill has liking, liking of Jill. We search the net with this, and if we find the match shown, we answer true. Otherwise, we answer false.
Let's pause yet again to have another look at general features of our mental model and the semantic net representing it. We find it very useful to give the net the property of segmentation. That is, it may be divided up into separate but related parts. And we then have a primary segment, which may contain subsegments, which in turn may contain sub-subsegments, and so on to any chosen depth, as shown to the left.
Each segment has the same properties. Each segment contains a semantic network which for various reasons needs to be separated from the other networks. The reasons for segmentation and how new segments come into being will become evident in what follows.
In part 1, we started to examine the concepts of definitions and instances. Let's look at a definition example first. Suppose we have a definition of a doctor along the following lines. The definition of a doctor is caring, a doctor is skilled, a doctor has a medical degree. So far we've not used the colon punctuation which is shown above. This may be used as a new segment introducer. In the net we add a segment using a new edge between the identifier and its members, as shown in the figure to the left.
Now looking at an instance example. Suppose we encounter the sentence, Jack is a doctor. The is, has, net of this sentence is shown to the left.
But since the definition of a doctor exists, then when we encounter the sentence, Jack is a doctor, we can automatically augment our mental model as shown in the net to the left-hand side by copying data from the definition into the mental model at this point. This mechanism in practice is not too dissimilar to using classes and instances in contemporary software languages.
Definitions may be nested. So as part of the doctor definition, we may have the sentence, "A doctor is a professional," as shown in the net to the left.
And then following on from this, we can have a definition of a professional. For example, we might say a professional is salaried, a professional is respected, and so on. So then when we encounter the instantiation, Jack is a doctor, a double augmentation takes place. Firstly, of the doctor attributes, and then of the professional attributes.
This slide shows the effect of the double augmentation. Again, not too dissimilar to using nested classes in software.
Let's have a look at definitions compared with Aristotelian logic. The following is often quoted as an Aristotelian logic example. So we have the phrase, "All men are mortal," followed by "Socrates is a man," and then the conclusion, "Socrates is mortal." But the left-hand figure shows it works also as a definition. So we start with "All men are mortal," which is an abbreviated definition of a man, shown in figure 1. Then we have "Socrates is a man," which is showing that Socrates is an instance of a man, shown in figure 2. And finally the conclusion, "Socrates is mortal," which in this case is shown as an automatic augmentation from the earlier definition, shown in figure 3.
Another place where segmentation is useful is in quoted or reported speech. So if we have the sentence, "Jack says Jill will carry the pail," which was dealt with in some detail in part 1, the resulting net is shown to the left.
Let's now switch our attention to a new and rather different topic, the topic of event intervals. Event intervals allow us to distinguish, if we so choose, between case perfect, as in Jack climbs up the hill, and case imperfect, as in Jack is climbing up the hill. They also give us a method of handling tense rather more precisely.
Looking at case perfect first. Figure A, left, shows climbing up, existing for a labelled 202 event interval. The interval duration itself need never be specified. If we have sequential activities, for example, Jack climbs up the hill. Next, Jack gets the water. Next, Jack climbs down the hill. Each may occupy a separate labelled event interval, 202, 203, 204, as in figure B.
By omitting the word next, we may put several activities into the same event interval. For example, Jack climbs up the hill, Jill watches Jack. Next, Jack gets the water. Next, Jack climbs down the hill. As shown in figure C to the left, the climbing and watching are made to occupy the same event interval, labelled 202.
Looking at case imperfect, this is represented by the sentence example. Jack is climbing up the hill. The climbing comes into existence at the label 202 in figure A and persists for an undefined interval. Other parallel events may take place in 202 to 205, say.
We may then terminate the climbing event at some later event interval by a sentence such as Jack isn't climbing up the hill, or perhaps a next sentence, as in next Jack gets the water. The first possibility is shown in figure B to the left.
In this lecture, we have only given a very brief overview of event intervals. Event intervals are flagged on the semantic network in a similar way to tenses. In practice, a separate set of event interval integers is held for each tense. Further discussion of event intervals lies in the realm of software and is outside the remit of this lecture.
Let's now have a look at yet another new topic. It's possible to view and manipulate part of our mental model whilst ignoring the rest. This is called localization. Let's just look at a few sentences on the following slide illustrating our own mental processes in this respect.
A control center has two control rooms. The first room is main. The second room is standby. Viewing the first room. We use this sentence to view only part of our mental model. The room has a supervisory desk and an incident desk. Note we say only room, not first or second room. Viewing the supervisory desk. The desk has a telephone and two screens. Again, we need only say desk, not supervisory desk. The centre has air conditioning, but we can still refer to an earlier topic centre if it can be unambiguously identified, leaving the supervisory desk. But we can go back to a step like this, leaving the previous or like this.
This slide shows the semantic net corresponding to the previous set of sentences. So looking to the left there, we've got the control center with air conditioning, and then in the central part we've got the two rooms, the main room and the standby room, and then over to the right hand side we've got the desk within the main room with a telephone and two screens, this desk being the supervisory desk. Also to the lower right there we've got the incident desk. Each viewpoint is effectively the root of a tree. So when we're moving from viewpoint to viewpoint, we search for a subnet and we start at the primary route. If the search fails, we try an earlier route, and so on. The dotted lines on the semantic network show the progress of these successive views.
Views and localization. This process of searching from a route, and then if the search fails, searching from an earlier route, as exemplified by 1 to 5 in the figure, mirrors processes used in the scoping of variables in contemporary software languages. But further discussion of the mechanisms involved really lies beyond the scope of this lecture.
Let's now have a look at sentence synthesis in a bit more detail. We can synthesize a sentence from our mental model by traversing a selected part of the model net. In this process, we may wish to stress certain topics in the sentence which emotionally we feel are important. We do this by applying so-called weighted anchors to the model, to the model nodes, to guide the traversal. To the left, the upper example stresses Jack, and the lower example stresses climbing.
There are one or two basic rules. Going forward via has, we get has in the sentence. Going backwards, we get of, but as noted in part 1, of is suppressed unless the previous node is a participle. Going forwards via is, we get is in the sentence. Going backwards, we get is by if the previous node is a participle, or of if not. Notably, if we ever backtrack through a node, we create a clause.
Using these rules, and starting at the node with the most stress, we get for the upper net to the left, Jack is climbing the hill. Note that we've suppressed the of in this sentence. For the lower net, we get the climbing of the hill is by Jack. Note the clause of the hill created by backtracking by the climbing node.
We might want to keep the stress on climbing, but stress Jack more and the hill less. These stresses are shown to the left and result in the sentence, the climbing by Jack is of the hill. Again, the clause by Jack results from backtracking via climbing.
We conclude this lecture by having a brief look at synthesizing a sequence of sentences associated with describing something. Similar mechanisms to views and localization are invoked when we are asked to describe something based on information in our mental model.
When we give a good, well-organized description, we tend to move progressively from the general to the more specific. This corresponds to going up our mental model tree, as in 1 to 8 to the left.
A less sophisticated way traverses the tree left to right, as in 1 to 7 in the figure to the left, and uses the view function successively on each tree branch. The result is shown on the following slide, which is actual output from the software application AI dialog following the request describe Jack. In this respect, Jack is assumed to be a doctor, and the definition of a doctor is also assumed to exist within the mental model.
There is just one Jack viewing Jack. Jack is a doctor, caring and skilled. Jack has a degree, viewing the degree is medical, leaving the degree, leaving Jack.
The directed graph structure. We pause here to consider a technical topic. The semantic network is what is termed a directed graph data structure. It consists of nodes and directed edges between nodes, as shown in the figure to the left. Each node, as we have seen, carries a label which is generally a single English word, but occasionally a quoted phrase. Each edge, in addition to its direction, carries data. This is primarily is, has or new, but also tense, for example past, present or future, and the event interval, which is an integer as previously described.
We can contrast the graph with a tree data structure shown to the left. With a tree data structure, we can only ever have one edge going into a node, and the edges shown dashed are prohibited. This has implications for any software we create to implement conversational AI. This software must be able to handle graphs rather than trees, which therefore impacts on its design. But this topic lies outside the remit of this lecture.
The isomorphic search. A particular requirement of the graph handling software is its ability to perform a search to find subnet matches within our mental model net. This is termed an isomorphic subgraph search for matches within the main graph, as shown below.
At this point, we've reached the end of the Part 2 lecture. Hopefully you found it interesting, informative and thought-provoking. There are just a couple of points to be made on the final slides which follow.
The software application AI dialog gives a practical demonstration of most of the theory described in the Part 1 and Part 2 lectures. AI dialog is able to engage in a conversation with the user, accepting plain English input and responding in the same. AI dialog comprehends user input and builds an internal mental model from this, of the type that we've been discussing. It subsequently uses the model to respond to user queries, testing this comprehension.
The AI dialog software application is protected by international copyright, but it is available as a free download for non-commercial private study purposes from a number of research data repository sites. It runs under Windows 10 and requires about 1 megabyte of memory. The publication mentioned on the final slide describes its operation and characteristics and lists the sites from where the download may be obtained.
Finally, the topics of both Part 1 and Part 2 of this lecture series are explored in much greater detail and rigour in the book published in 2021, Artificial Intelligence That Can Comprehend, authored by myself, and which is available from Amazon.com.